All right. Hello, everyone. My name is Sebastian. I'm at the University of Munich, and I'm heading the Quantum Applications and Research Laboratory. And I would like to give a side report on the QAR-Lab. And this is the third side report. We did it as well last year in Milan and also in Munich. And also with me is my colleague Thomas, Chris, Sebastian, and Claudia. All right, so the talk is divided into 4 parts, and I would like to give an update on our project called Planck. We have some insights regarding some neural network strategies. We try to perform archetypal analysis on the D-Wave machine, and we try to find the Holy Grail. Let's see what I mean with this later on. So, the Planck project, this is an abbreviation in German for Platform and Ecosystem for Quantum Supported Artificial Intelligence. It's funded by the Federal Ministry of Economics, and it started in the beginning of this year. You can have a look at the website. There's an English version as well. And we have a consortium with several partners from the universities, Berlin, Stuttgart, but also from vendors and companies. And also we have some associated partners we are very proud of. And the basic idea behind this project is that we would like to create and promote an ecosystem that performs quantum AI as a service. The idea is that there are several stakeholder work together. So we have, for example, generic quantum AI concepts, and they get analyzed and standardized by by specialists and the community. And then we have some quantum algorithms. They get implemented by developers. And then we have some quantum AI application. They can be searched and ordered by users. So we have some packaged solutions. This is our idea as a quantum AI as a service. And we had, like I said, the kickoff in the beginning of the year. So there's some updates on this. We completed the requirement analysis of the industrial use cases. We started the implementation and the integration of some QAI algorithms into the platform. And we are proud to say that the first platform prototype will launch in the end of this year. And to give an outlook, also we are proud that we can welcome some additional partners from the industry in our consortium in 2021. And if you'd like to have some further information, please visit our website. The next part I would like to talk about is our paper about neural networks, and it goes like that. Everyone, I guess, knows the traveling salesman problem. So you have a weighted graph, for example, with these 7 vertices. You have a weighted graph, and you would like to have a route through every node, such that the total costs are minimal. And there is also a QUBO formulation for this. This is just a snapshot, a small snapshot of this matrix. It's much bigger, and this is the problem. So we have the problem that the QUBO matrix is too large. It is too large to put it on this previous slide. This was just a small zoom in. It is, I'm sorry for that, too large for the current hardware. You can just solve some smaller graphs, not ones with several hundreds of vertices as you need to. And the fact is that the QUBO matrix is way too large compared to its content. And then we got the idea, what if we train neural networks to help us with processing that matrix? And this paper I would to highlight and sketch here is exactly about that. So I would like to present 4 results on that. And the first thing is we used autoencoders. Autoencoders work like that you have something and you try to encode it into a latent space. And from this latent space, you try to decode it as good as possible. So the autoencoder just remembers the most important things. So we used a trailing salesman problem as QUBO formulation, encoded it into the latent space, and decoded it as good as possible. And then we had a look at the latent space. And so the autoencoder did quite well. So the autoencoders can strip redundant information out of this QUBO, and this redundant information are generated during the TSP to QUBO translation, at least for example. And the impact is quite nice. If we know what redundant information are and not redundant information, important information, then we can use autoencoders to identify some inherent complexity in certain kinds of QUBOs. So if the autoencoder is not able to reconstruct it, then it is too hard for the system, let's say. Then we tried, of course, the straightforward way solving TSPs out of QUBOs. We take a QUBO from a TSP and solve it into a solution. The preliminary result, yes, neural networks can solve TSPs even when given in QUBO form. And yeah, of course, we expected this. Then we tried to solve TSPs indirectly. So we took a traveling salesman problem as a QUBO, encoded it into the latent space, and the latent space were pushed into the solver network in order to find a solution. And the preliminary result is that this neural network can solve TSPs even if it's given in this latent space encoding generated from instances in QUBO form. So this verifies again that the latent space encoding retains enough information to solve TSPs. And the last one is that we pushed QUBOs into the solver net to solve it, but not TSP QUBOs, but arbitrary QUBOs. So it was arbitrary quadratic programs, and we tried to find a minimum of that. And yes, the preliminary result is that neural networks can solve general QUBO problems to some extent. And so the impact is that neural networks could be used as QUBO solvers for certain instances. Yeah, we wrote a paper, it got accepted, and you can have a look at this. It was accepted at the QSE, it's on Archive, and yeah, the next steps is to design a united interface for the complete toolchain. We would like to use neural networks not only for solving QUBOs, but for the pre- and post-processing, and would like to evaluate furthermore the performances and weaknesses. Okay, so after talking about Planck and neural networks, I would like to go into archetypal analysis. Archetypal analysis is a fuzzy clustering algorithm, and it works like that. Perhaps as an example, as a motivation, there are archetypal soccer players. There are defenders, strikers, midfielders, goalkeepers. There is the striker, there's Messi, for example, or we have a the goalkeeper Manuel Neuer, for example. But this is not a good example because Manuel Neuer is not only a goalkeeper but also a striker, I guess. So what I would like to say is you have some extreme data points or some extreme types of soccer players, and all other players are assigned to one category or to a combination of these. And more as a visualization, on the left-hand side, you see in the 2D plane some data points and the convex hull around them. And if one says, all right, please give me the two most extreme data points, then it could something like these 3 points. And this is archetypal analysis. It deals with finding these extreme data points. And it works like that we try to optimize something, to minimize something. Given X, these are our data points, we try to find the best assignments to the best archetypes, plus some constraints, convex hull, etc. I won't talk about it. So basically, given data points, find the right assignments to the right archetypes. And this is what archetypal analysis does. And we tried to think about a way to approximate this. The intuition behind our paper is we asked ourselves, what makes a good choice of archetypes? On the left-hand side, you have two examples, some data points in black, and then we have this 3 green archetypes and 3 blue archetypes. And just from looking at it, one could say that the 3 green archetypes are better than the other ones here. So perhaps it's not necessary to perform this complex minimization. Perhaps just find large distances between the archetypes. And this is what we did. We approximated this convex hull approximation, one can say. Our algorithm contains of 2 parts. The first part is on selecting k data points as archetypes that have maximal distances. And the second part needed to be done for each data point. It goes around the assignments. Minimize the deviation of the data points from its representation as a convex combination of archetypes. This is the constraints that I talked about. So we have these 2 parts, and we did it on the quantum annealing machine, and we got quite nice results, even though we did not solve the actual problem, but a relaxation of that. So just to give you an impression, on the left-hand side, you see again this toy data set with in black points with the convex hull, and the green lines are the approximation of the convex hull with the archetypes. This is the original R package archetypes. And on the right-hand side, you see our approach, our quantum annealing approach, and it looks similar. And it gets even better when using, when say, dear algorithm, please get me k equals 5 archetypes. This idea was accepted by the conference ESAN, and it will be presented on an online conference next week or so. To conclude, yes, the QUBO formulation, or to approximate the archetypal analysis via QUBO formulation, is possible. And for some data sets, we got results that were comparable, not better, but we got into the direction of the original algorithm. So there's some further work to do. And now we go into the 4th part of this talk. It's about the Holy Grail. I guess we can all say that there is an overwhelming speed of new developments regarding both. First, regarding machine learning and artificial intelligence. So there are no algorithms where one can, where they are able to master some real-time strategy games, what is very complicated. On the other hand, we have some, very good developments regarding quantum side. You see it at least at the paper, the quantum supremacy paper that got published. So I guess there's some vast possibilities and grand challenges that may guide us to a fruitful convergence of AI and QC, and I would like to elaborate more on this. So QAI and AIQ. Quantum AI uses quantum-inspired algorithms to solve AI-related computation tasks, but you can use it the other way around. You can use AI methods to better approximate quantum computations. So in May last year, there was this workshop or something, machine learning for quantum technology. Exactly like I said, AIQ or MLQ, machine learning for quantum technology, not the other way around. That's quite nice. And in our opinion, there are 2 main reasons that Q and AI may end up highly synergetic. First, the point randomness, and second, the point complexity. So first, randoms for synergy, randomness. Most machine learning methods need some randomness to work. They put serious effort into generating entropy. They show high tolerance against noise. So randomness and noise. And so you see, this is inherently suitable for the early application of NISQ hardware. You have some randomness in there and you have a lot of noise. I mean, the N stands for noisy. And the second reason, I guess, is the progress in AI is really demanding regarding the computational resource. And it gets even harder and harder. So there's the need for new kinds of compute power. So this in our opinion, are the two reasons for the synergy. And there's some work in the field of quantum assistive AI, and we performed a survey on available quantum AI algorithms, and we saw that one can try to group them into 4 groups. First, the mathematical operations, for example, variational quantum eigencells, HHL. Then we have some traditional machine learning algorithms like clustering, SVMs, etc. Some algorithms that go into the optimization part, like QAR, QUBO, and neural machine learning, Boltzmann machines, autoencoders, etc. And we had a look at the papers, and we saw, or we made a table where we said the algorithm or the task, and then on which quantum computing platform they run on, if we, if there's an implementation available, and if we think if this algorithm is fit for being used on NISQ devices. And then we saw or imagined where this quantum task could fit in a machine learning pipeline. So we matched it to a machine learning pipeline. And the thing is, here, this is an example of a machine learning pipeline. There are several other machine learning pipelines as well, but you see the requirement transformation, reward engineering, hyperparameter optimization. Also, here's some other topics, but what I would like to say is the quantum algorithms that we found focus, of course, on computationally expensive tasks. First, at the data and domain part. This is computationally expensive. You need to model and sample complex probability distributions. And on the training part, where you have to execute lengthy update operations on matrices, etc. So you see, we have here some algorithms that help at the red circles, but there are a lot of other parts in the machine learning pipeline that are not covered by quantum algorithms. So currently we think that many classical machine learning steps are necessary. This is still hybrid. So when I talked about the needs of AI and the current state of QAI, so we can say that there are some major challenges, and we think there are 4 major challenges. First, the feedback loop. Replace the feedback loop around the training entirely with quantum algorithms. In our opinion, this is the holy grail. This is really the holy grail for helping the model on policy selection for training and assessing the quality of service. This would be great. The next challenge is the training data. How to provide algorithms that process huge data or the essence of huge data on quantum computers. The interfaces, as often, how to provide standardized interfaces for the combination and collaboration of hardware, software, and people. And I like that one, the real reason. Keep track of the source of the observed improvements. What gave you improvement? So to conclude, there's on the archive as well, a preprint. QAI might end up highly synergetic because of the randomness and the complexity. And there are some major challenges, namely the feedback loop, training data, interfaces, and real reason. All right, so this was what I would like to talk about, and I say thank you for that. Also in the name of my colleagues, and say thank you and goodbye.